Hi folks, welcome back to another lesson, and we're moving on to a slightly new topic now, which is about nuclear radiation. So hopefully you'll find this topic fairly straightforward compared to some of the other stuff does. It's a very nice, well-contained topic, and some of it will also cross over with your chemistry and stuff that we did in Nat 5 as well. So it's about nuclear radiations, and we look at how to identify the atomic number, proton number, and mass number. If you do chemistry, you'll find that really straightforward. We're going to state and explain what radioactive decay, alpha, beta, and gamma radiation are, which kind of crosses over a little bit with the standard model, and then write down equations that describe radioactive decay releasing alpha, beta, or gamma radiation. So a fairly short kind of summary there, folks. So first of all, what are the parts of the atom? Hopefully you can tell me what they are or draw a wee diagram, but so pause the video and have a wee go of it, but this is what I'm expecting. So we have the electrons, which are negative, mass nearly nothing, and they orbit around the outside of the atom. The proton, which is positive, same mass as the neutron, which we say is 1. And the neutron, which is neutral, and it has the same mass as the proton, so we say it's got a mass of 1. So that's a basic model of what an atom looks like. Now, mass and atomic number, if you do chemistry, you know how to do this bit, but I'm just going to go over it fairly quickly for those who don't. But essentially, we have proton, neutrons, and electrons, and they have a relative mass of 1, 1, 0, and a relative charge of +1, 0, -1. Now, the reason why we say it's a relative mass and a relative charge is because we're comparing them to each other. So we're assuming, for example, that the proton has a mass of 1, then the neutron compared to the proton also has a mass of 1. The electron compared to the proton has a really, really, really small mass, and that's why we say relative to the proton, it has a 0 mass. It's not that it has no mass, it's just that compared to the proton, it's so small, we can kind of say it's 0. And then the relative charge, as you probably know, protons are positive, electrons are negatives, and neutrons are neutral. Now, how do we record this in terms of different elements? Well, we've got an element here, helium, and we've got these numbers 4 and 2. So the way this notation works is that the number on the top right is called the mass number, and it's given by the number of protons plus the number of neutrons. The letter in the middle is the symbol, and all of these are given in your data sheet, because in the back of your data sheet there's a periodic table with all the symbols of the different elements on the atomic table with their mass number, and the next bit, which is their proton number. Okay, so if you can read this and you remember this, we will always know the proton number, and because we have the mass number, we can always work out the number of neutrons as well. The final thing is that we assume that all the elements shown in an atomic table are neutral. So if you know the number of protons, you automatically know the number of electrons as well. So check if you understand that, how many protons and neutrons. So if we go through this one, okay, so pause the video after each one and try it. Hopefully you get that it's 1 electron, 1 proton, and no neutrons, because remember, there's 1 proton here. So if the mass number is 1, then it must be 1 proton plus 0 neutrons. We're assuming it's neutral, so it's 1 electron. Okay, so try these ones, and I will go over the answers with you at the tutorial. So have a go at this and see if you can figure out what the number of protons, neutrons, and electrons are. Now, isotopes. An isotope is an atom with the same number of protons but different number of neutrons. Okay, and remember, you can't change the number of protons because the number of protons define what an element is. So what I mean by that is hydrogen because it has 1 proton and 1 proton only. Helium is helium because it has 2 protons and 2 protons only. If you took one of those protons away from helium, it then becomes hydrogen. Now, going back to isotopes, the isotopes always have the same number of protons, so that means it's always the same element, but the number of neutrons can change. So their chemical properties are the same, but their nuclear reactions are different. And this is where we kind of diverge a bit from chemistry. So an example of this are the isotopes of carbon. So carbon can exist as carbon-12, carbon-13, or carbon-14. And notice for each of these, the number of protons are the same, but it's the number of neutrons which are different. And in fact, carbon-14 is really famous because we use that in radiocarbon dating to predict the age of different objects. So there's a wee joke there for you folks. Okay, now, as physicists, we're quite interested in isotopes of hydrogen because these are the ones that react in a sun under nuclear reaction to give it energy, etc. And we'll talk more about that later on. So the three types of hydrogen that you will come across are protium, which is simply a hydrogen which is made up of entirely one proton and an electron, so no neutrons. Deuterium, which means there's a proton and neutron. Tritium, which is a proton and two neutrons. And the idea here is that du means kind of two, tri means three, think of a triangle. And so these are the isotopes of hydrogen. And you can use these isotopes to make water, and this is where the term heavy water comes from, because heavy water is usually made from tritium because it has an extra neutron. That water is heavy. And heavy water actually has different chemical properties from normal water, and it's been proven that if you grow plants with heavy water, they don't grow as well as, say, with usual water. Okay, now, here's where the nuclear decay comes in. Isotopes can become unstable and spontaneously decay, and this results in the release of radiation. And remember, spontaneously means it happens without rhyme or reason. Now, the three types of radiation that you've used before are alpha, beta, and gamma, and these are the three symbols that we use to represent them without having to spell the full words out. So what are the three types of radiation? Well, let's look at them in turn. So alpha decay is literally a particle that is a helium nucleus with its two electrons removed. So the symbol for it is He42 2+. 2 at the bottom because it tells us it's got two protons. Mass number of 4, which tells us it has two protons and two neutrons. We have the 2+ here because it tells us we've actually removed the two electrons from the helium atom. So that means alpha particles are actually positively charged. So a lot of information there for you to take note. I would write some of those down. So it contains two protons and two neutrons and no electrons. Okay, so what is the nuclear equation for alpha decay? Well, if we look at it, here's a general equation. Let's see how we got this. X is some element with a mass number and atomic number. Now, if we emit alpha radiation, we're going to lose two protons and two neutrons. So that means our new element will be two protons less and a mass number of 4 lighter. Because remember that mass number, you're going to be losing two protons and two neutrons from it. So that's why it's a -4. Now, this is the general equation for alpha decay. You're expected to know this, and you're expected to know that if there is alpha decay, your mass number decreases by 4 and your atomic number decreases by 2. So this is an unstable atom. It decays to give us a more stable atom, but it has to release alpha particles to do that. And a final thing is that the total of the atomic numbers on the left-hand side must equal to the total of the atomic numbers on the right-hand side. And the same is true for proton numbers. So what does that mean? Well, what that means is if you add all of this number and this number on the right-hand side, you must still get the same answer, which we do, because remember, A minus 4 plus 4 gives us A. Same with the proton numbers, Z minus 2 plus 2 gives us Z. We don't do this number here because we don't have it here or here, so we can ignore those. So there are lots of ways for you to check that you've got the right nuclear equation. Now, an example of alpha decay would be, for example, an element called radium, which is radioactive, and that's unstable to decay into two other elements. I think this one's called radon and helium. And notice we've lost the helium, so that's why the mass number drops by 4 and the proton number drops by 2. Alpha decay, to summarize that, we have the general equation for alpha decay and an example of it, and that's what you need to know for alpha decay. So try these yourself to see if you can work out what the missing quantities are. And this is very typical of an exam question that you get. So pause the video and see if you can work out what the missing numbers are, and I'll show you the answers on the next slide. Okay, so check your answers, make sure they're correct, and then we're going to move on and look at beta decay. So beta decay, you may remember from the standard model, it's a process by which a neutron is converted into a proton. And it's really important because it allows new elements to be made. And you may remember as well, you get an antineutrino released and an electron. And it's this electron here which is the actual beta radiation. So how do we describe beta radiation? So beta radiation is when a fast-moving electron is emitted from the nucleus of a decaying radioactive atom. And so we've got an unstable atom, and it releases an electron. And remember, beta decay occurs when a neutron changes into a proton, releasing an electron and an antineutrino. So what's the equation for beta decay? Well, it looks like this. It will have one less neutron and one extra proton. So for beta decay, the proton number said increases by 1. The mass number stays the same, but the neutron number decreases by 1. Because remember, the neutron is converted into a proton, but they both have the same mass. So the proton number increases by 1, the mass number stays the same. So here's how the equation looks. Remember, this is our unstable element. This is the new stable element, and this is the beta radiation. And again, notice if you add the numbers along the top here, you should still get the same as the left-hand side. You add the numbers along the bottom left here, you get the same as the left-hand side. And I forgot to mention this, but this is just a conservation rule. So it's a conservation of proton numbers and the conservation of mass numbers. So here's an example of beta decay. Notice here how the mass number stays the same, but the proton number has increased by 1. And again, notice that if we add the 85 to minus 1, we get 84, which is the same as the left-hand side. The 218 plus 0, we still get 218. So we have that conservation of proton and mass number. And again, you're expected to know these equations, so I would make a note of these. So as always, let's just show you what these examples look like. So this would be polonium, and that could decay to actinium and beta radiation. And again, notice how the numbers fit our general equation for beta decay. So as always, let's check for your understanding. See if you can do these 4. The answers are on the next slide. So pause the slide, have a go of it, and let's check your answers. Okay, again, pause the slide and just check that you've got the right answers. And the final one we're going to look at is gamma decay. Gamma radiation is an electromagnetic wave, so it's kind of like the odd one out. It has no mass with charge and does not affect the atomic number or the mass number of the isotope. So we represent that simply by saying, here's the unstable element, here's the unstable element afterwards, and it's given out a gamma radiation. So notice the proton and mass number are 0 because it's an electromagnetic wave.